الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمراً مهماً عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمتنا.
السلام عليكم ورمضانكم مبارك. إن شاء الله تكونوا كامل بخير. معكم محمد عمروش, Geoscience Group Leader from INAS, and نرحب بكم في another webinar this month in April in our new project. يعني بدينا هذا العام project جديد اللي هو Advances in Geoenergies and Renewables, where we are going to cover different aspects of geoenergies and renewable energies, inshallah. So in this month, we are very happy to have our fourth webinar, and our keynote speaker is going to be Dr. Hamid Zentou. Assalamu alaikum, Dr. Hamid.
وعليكم السلام ورحمة الله وبركاته. رمضانكم مبارك. شكرا لكم على الاستضافة.
يعطيك الصحة. شكرا على thank you for accepting our presentation. يعني Dr. Hamid Zentou is a postdoctoral fellow at the Advances Members and Porous Materials Center at the King Abdullah University of Science and Technology in Saudi Arabia, KAUST. He received his bachelor and master in process engineering from the University of Khamis Miliana in Algeria in 2021. He was awarded a PhD in chemical engineering from University Putra, Malaysia. He has published 14 articles and was signed as a reviewer for different journals in the chemical engineering field. He joined in 2022 King Abdullah University of Science and Technology, KAUST in Saudi Arabia, and his primary research interests lie in the field of membrane separation modeling and optimization. So today, Dr. Hamid is going to share with us the biofuel alternative for the renewable energies. تفضل Dr. Hamid, the floor is yours. Thank you very much.
Okay. First of all, thank you very much for inviting me here. Thank for INAS for this space to share knowledge between the Algerian scientists in Algeria and abroad. I am happy to be here today to present these projects entitled Towards Sustainable Biofuel Production and the Integration of Membrane Technology in Biofuel Industry. In this short presentation, we will try to cover three main points. We start with overview of bioethanol production in the world. Then we pass to talk about alternative techniques for bioethanol recovery. Then we take like case of study about integration of membrane technology in bioethanol. And we talk about the integration of perforation for bioethanol recovery during the ethanol production. Okay, so we start with overview of bioethanol production in the world. Here, as we see here in the picture, one of the main challenges that we are facing today in the planet is the global warming. Usually in the natural case, when we receive rains from the sun, and we receive this heat from the sun, and this heat is very important for the growth of the plants and for the life in the earth. But nowadays we see that the heat is over the natural temperature that we used to have maybe in previous years. And this will accumulate a lot of problems that the Earth experience right now. Maybe when you see the picture here, it's like the satanic face of the sun. You think that the sun is the reason behind this situation, but actually the responsible about what's happening is living here, somewhere here in our planet, is the human being. Okay, so the global warming actually is one of very dangerous phenomena that threat the life on the earth of and we mean the life of humans and the life of other living beings like planets and animals. Okay, so as we said, that the global warming, here I wrote the global warming, actually is not a mistake of spelling, but actually global warming need global warning because it's very threatening our life here. So I said that the responsible behind the scan is the humans. We consume a lot of petrols, and the petrol usually will produce a lot of carbon dioxide. And this carbon dioxide and other gases make like a barrier which stop the heat for escaping the earth. So they keep this heat, as we just forgot to escape this. Here, when we see here, usually in the natural case, when we receive some heat from the sun, majority of this heat will be reflected on the space. But recently, because the emission of these gases will form like layer or cover, which keep the heat and stop it from escaping from the earth, as we see here, which make the earth warmer. And this is what we call it, the global warming. Okay, so we said that the consumption of petrol and in the industry and in the maybe using for transportation is the main reason which caused global warming. This global warming can lead to different problems in our planet. For example, we said that we experience higher temperature than the usual that we know maybe for previous decades. At the same time, we see that there is like a changing of climate, and we are experiencing, for example, even maybe you are in Algeria right now, and you see that we are experiencing winter in summer and summer in winter. There is this a result of the global warming. We see here the melting of glaciers, and we see, for example, here the oceans gets warmer and warmer, and this can cause a lot of problems. إذا نحكوا على الاحتباس الحراري. الاحتباس الحراري عنده عدة تبعات، من أهمها أنه اختلاف في الجو. على سبيل المثال هذه الأيام نشوف في الجزائر أنه الجو شتوي وإحنا على مقربة الصيف، ومرات فترات يعني في فترات الشتاء وإن كان الجو مماثل لجو الصيف. وهذا من أحد النتائج أو تبعات الاحتباس الحراري. في نفس الوقت الاحتباس الحراري هذا يؤدي إلى ذوبان الجليد في القطب الجنوبي أو القطب الشمالي، وهذا يؤدي إلى يعني وفاة أو اختفاء عدة أنواع من الحيوانات اللي يمثل بالنسبة لهذا القطب الجنوبي يعني ملجأ. وهذا يؤدي أيضا إلى ارتفاع حرارة المحيطات وارتفاع مستوى البحر، حتى أنه بعض الجزر في المحيط الهندي والمحيط الهادي مهددة يعني أنها يتم إغراقها عن طريق المحيط، مثل جزر المالديف على سبيل المثال. So in this difficult situation, renewable energy to substitute, usually, so we said that the consumption of fossil fuels like petrol is the main reason of the global warming. So it is very important to look for new sources of energy. Currently, we have different renewable energy that can substitute or at least limit the use of petrol. For example, we have biofuels, we have the wind power, the solar energy, and at the same time we have the hydropower. In our case here, or of study, we'll focus more on bioethanol, which usually generated from biomass. Okay, so we have three different types of biofuel, or three generation of the biofuel. The first generation usually is made from food crops like sugar and corn, and we have the second generation, usually is produced from starch and cellulosic feedstock and agriculture wastes. And we have the third generation biofuel. It's made from the microalgae and macroalgae. And we have also the last generation is called fourth generation. Usually we use engineered metabolic and we have genetic modification to produce some kind of algae that can produce some type of biofuels. Okay, so when we talk about the biofuels, there is like three types or two types. The major types of biofuel are bioethanol and biodiesel. For bioethanol is represent around 66% of the total global production of the biofuel, and the biodiesel represents around 26%, and we have around 8% is hydrogenated vegetable oil. In the picture here, we see the global production of bioethanol. So we see that United States is the pioneer of the production of bioethanol in the world. Then it's followed by Brazil, and we have European Union, and we have Canada, and it's followed by China and other Asiatic countries like Thailand and India. إذا في الصورة هنا توضح الصورة يعني الخريطة الإنتاج العالمي للبايوإيثانول. هنا نشوفوا أن الإنتاج العالمي أو أمريكا الولايات المتحدة الأمريكية تمثل المنتج الرئيسي للبايوإيثانول في العالم، متبوعة بالبرازيل والاتحاد الأوروبي. ومثل ما شفنا من قبل هنا شفنا أنه في عدد مصادر مختلفة للبايوإيثانول. نشوفوا على سبيل المثال هنا المنتوجات الزراعية مثل قصب السكر، مثل البطاطا، مثل الذرة. وشوفوا من الجهة الثانية الجيل الثاني من الوقود الحيوي عادة يكون عن طريق تخمير النشا أو السيلولوز، والجيل الثالث عادة يكون عن طريق استعمال الألغاي. إذن حتى هنا الدول نشوف أن الدول هذه كل دولة تتميز بنوع مخصص أو بمصدر للبايوإيثانول مختلف. نشوفه على سبيل المثال الولايات المتحدة الأمريكية على سبيل المثال المصدر الأساسي للبايوإيثانول هو الذرة. نشوفه على سبيل المثال بالنسبة للبرازيل المصدر الأساسي للقصب هو القصب السكري، ولما نشوف أوروبا على سبيل المثال المصدر الأساسي لإنتاج البيو إيثانول هو القمح. لما نحكي عن القمح نقصد به التبن. إذن هذا كان بصفة عامة نظرة عن الإنتاج العالمي للبيو إيثانول. حاولت خلال العرض هذا البحث عن مصادر عن إنتاج الجزائر عن الوقود الحيوي، لكن تفاجأت أنه كل المصادر تقول أن الإنتاج صفر. هذا ممكن رغم أني طلعت في عديد من المصادر أو حتى المقالات الصحفية والمقالات على التلفزة والميديا أنه في مشاريع كثير في الجزائر على البايو إيثانول، خاصة استخلاصها عن طريق بقايا التمر. بعض المشاريع الجيدة شفتها، لكن ممكن لأنه هذا الإيثانول ممكن موجه لاستعمالات ثانية، ممكن الاستعمال الطبي أو أشياء أخرى، لهذا كان عادة مش موجه للاستعمال كطاقة بديلة. وهذا نظن هو مبرر النتائج اللي تحصلت عليها أنه إنتاج الجزائر منعدم في إنتاج البيو إيثانول كطاقة بديلة. Now we want to ask, why does Algeria need to establish a program for the development of bioethanol industry? So all of us, we know that Algeria is a petroleum country, and we think why we need another source of energy or bioethanol, for example. As we see here, هنا نشوف قائمة من الأسباب التي تدفع الجزائر للبحث أو لتأسيس برنامج لتطوير الطاقات البديلة أو طاقة الإيثانول كطاقة بديلة. عائدات الجزائر انخفضت بحوالي 50%. لما نحكي على عائدات الجزائر من مداخيل البترول على سبيل المثال، نشوفوا بين سنتي 2015 و 2014 كان فيه انخفاض حوالي 50%. كانت حوالي 34 مليون دولار سنة 2015، بينما كانت حوالي 68 مليون دولار في 2014. لهذا يجب البحث عن طاقة ثانية أو مصدر للطاقة الثانية، وفي نفس الوقت هو راح يكون أداة للتنمية، توفير مناصب شغل. ولهذا البرنامج لتطوير الطاقات البديلة وخاصة البايو إيثانول هو شيء مهم للبلد. السبب الثاني يدفع الجزائر للتركيز على الطاقات البديلة أنه نوعية أو جودة الهواء في الجزائر تتميز بنسبة عالية من التلوث. هذه النسبة تتجاوز حتى الدول المتطورة مثل ألمانيا وفرنسا حتى الولايات المتحدة الأمريكية، رغم أن هذه البلدان معروفة بأنها دول صناعية عندها منشآت صناعية أكثر من الجزائر. لكن نشوف أن الجزائر فيها نسبة كبيرة من التلوث. هذا التلوث عادة يرجع بصفة عامة إلى استعمال السيارات، المناطق الصناعية، وفي نفس الوقت يرجع إلى حرق المخلفات الصناعية أو المخلفات الزراعية أو حتى المخلفات الغابات اللي عادة في الدول المتطورة يستعملوهم لإنتاج أو الرسكل. إذن لهذا البايو إيثانول أو الوقود الحيوي راح يساهم بنسبة كبيرة في خفض هذا التلوث عن طريقين. الأول عن طريق تقليل من استعمال الوقود الأحفوري اللي هو البنزين أو البترول العادي اللي نستعمله في الأيام العادية، وفي نفس الوقت راح يساهم في خفض هذه الانبعاثات من خلال استعمال هذه البقايا ورسكلتها لإنتاج البايو إيثانول عوضا عن حرقها. السبب الثالث الجزائر حاليا يعني 2020 تحتاج حوالي 21 مليون طن oil equivalent من الطاقة، لكن نشوفوا أنه هذا الكمية يعني في 10 سنوات راح ترتفع ب50%، يعني حتصير حوالي 91 مليون طن oil equivalent بعد 10 سنوات. وفي هذه الحالة يعني قدرة الجزائر على تصدير البترول راح تكون منخفضة، وراح تكون موجهة بنسبة كبيرة إلى الاستعمال أو الاستهلاك المحلي. هذا الاستهلاك المحلي عادة الارتفاع أو النشاط الاقتصادي، في نفس الوقت لارتفاع population أو زيادة عدد السكان. وبزيادة عدد السكان راح نحتاج إلى طاقة أكثر، وبالضرورة يعني يصير الإنتاج الجزائري موجه للاستهلاك، وتكون كمية قليلة موجهة للتصدير. لهذا يعني الجزائر تصير مجبرة لاستباق هذه الحالة من الآن للبحث عن مصادر بديلة للطاقة. The Algerian agriculture uses only 70% of the national territories, which is about 2,380 million hectares. بدنا نشوف الجزائر بلد واسع، يعني في حوالي 238 مليون هكتار، فقط 17% من هذه المساحة المستغلة حاليا للزراعة. يعني في حوالي 83% يمكن استغلالها في الزراعة الزراعة اللي تكون موجهة للبايو إيثانول على سبيل المثال، مثل القصب السكري، مثل أشياء الذرة، يعني فيه مساحة واسعة. بالإضافة إلى ذلك الجزائر تتوفر على عديد من المصادر التي يمكن استعمالها كمصدر للوقود. نشوفوا على سبيل المثال في الشمال عندنا التبن في الجزائر. نعرف أن زراعة القمح منتشرة كثيرا في الجزائر، يعني الويت سترو هذه ممكن استعمالها في إنتاج البايو إيثانول. نشوف في الجنوب منطقة معروفة بإنتاج التمور، هاي بقايا التمور في نفس الوقت يمكن استغلالها في إنتاج الوقود الحيوي أو البايو إيثانول. في نفس الوقت بقايا الغابات يعني تريز، هذا ممكن هي مصدر للسيلولوز يمكن استعماله في الإنتاج. مولاسز اللي هي البقايا أو البايو برودكت من صناعة السكر، يعني بعض البقايا من صناعة السكر يعني عوض رميها يمكن استغلالها في إنتاج الوقود الحيوي. حتى نشوف مناطق في الجزائر في الشمال معروفة كثير بزراعة الزيتون وإنتاج زيت الزيتون. خلال إنتاج زيت الزيتون موجودة كثير بقايا صلبة، هذه يمكن استعمال هذه البقايا الصلبة أثناء بعد يعني إنتاج زيت الزيتون، يمكن توجيهها لإنتاج الوقود الحيوي. يعني نشوف هنا أن الجزائر من خلال مساحتها، من خلال الموارد المتوفرة عليها، تتوفر على إمكانيات تؤهلها لتصير دولة رائدة في إنتاج الوقود الحيوي. ممكن في فترة من الفترات كان هذا خيار، لكن مع الزمن هذا الشيء يعني لن يكون خيار. will not be optional, but it will be compulsory to devote our effort in this way. Here we highlight some challenges that related to the bioethanol industry in the world, especially in developing countries. So we see that we talk about the bioethanol industry to be alternative to the petrol maybe over a decade, but we don't see that in reality. So this is because of different challenges. So some of these challenges is the influence of bioethanol sector on food security. For example, we have talked about that bioethanol is produced from different agricultural crops like wheat, for example, corn, but this can make like competition with another crops that is devoted for the food for poor people. For example, I know, especially for example in some African countries. So it will be not fair to specify this land for planting industrial crops for bioethanol rather than specify or make this land for making the food for these poor people. So في هذه الحالة على سبيل المثال الدول الفقيرة يعني صعب أنه تخصص هذه الأراضي لزراعة صناعية لإنتاج البايوإيثانول، بينما هي تعاني من أزمة في الأمن الغذائي. يعني هنا نشوف منافسة أو نحل مشكل ونقع في مشكل يكون هو أخطر. The second reason is, or the second challenge is the absence of financial support. So usually the financial support from the policymakers is one of the challenges that the bioethanol industry facing, especially in developing countries. Another challenge or one problem that is related to bioethanol industry is that the biofuels may release more greenhouse gases than they help to conserve. How we explain that? For example, yes, biofuel can reduce the emission of the carbon dioxide, but at the same time, for different countries, they need to cut the forest. They need to cut the trees, what we call it deforestation. So this deforestation is needed to plant some crops that will be used later for bioethanol industry. And here it doesn't make sense. We are reducing the consumption or the production of the carbon dioxide, but at the same time, we are going forward in deforestation. So على سبيل المثال هنا نقطة أنه البايوإيثانول حقيقة يخفض من انبعاث غاز الكربون دايوكسيد، لكن من جهة ثانية بعض الأراضي على سبيل المثال في البرازيل في الأمازون وفي جهات ثانية في العالم حتى يقوموا بزرع هذه المحاصيل لتوجه لإنتاج الإيثانول، هنا يحتاجوا إلى قطع الأشجار وقطع الغابات حتى يتم زراعة هذه الأراضي بزراعات توجه لصناعة الإيثانول. وهنا يكون فيه تناقض، من جهة يعني احنا نحاول نخفض انبعاثات، ومن الجهة الثانية نقطع الأشجار اللي هي أساسا تمتص الكربون دايوكسيد وهي أساسا تخفض هذه الغازات في الجو. لهذا أنا من الضروري أنه إنتاج الإيثانول يحاول يعتمد حتى يكون صديق، عنده مفهوم صديق للبيئة، يكون موجه أو يكون يعتمد أساساً على البقايا الزراعية أو البقايا الصناعية، أو في نفس الوقت لأنه في هذه الحالة يكون عنده مصداقية أكثر. وفي هذا المجال لازم يكون فيه تعاون. يعني when we talk about the production of the industry, we need we consider like the wheel, and this wheel has three components, which is the public, the academia, and policymakers. The public, they need to help in recycling, for example, and they need to contribute in the program of development of bioethanol. At the same time, the policymaker need to implement policies that motivate this industry, and at the same time to support the academia by financing these projects. And the academia at the same time, when I just really something that maybe very important. For example, we can see in Algeria or different countries, we can find like thousands or millions of papers and articles published for producing bioethanol from different feedstocks. But when we go to the reality, we don't see the implementation of this project in reality. So, and because there is big or large gap between the academia and the same time in the industry. So we must, or we should narrow this gap to make or to motivate the industry to implement these projects from the papers to the reality. So the academia, one of the maybe most important gap is the absence of techno-economic analysis of the projects that we published or working on, and we keep it in the lab scale. So to maybe apply these notions and this result on industry scale, we need techno-economic analysis. So على سبيل المثال لما نحكي على الأبحاث التي نشرت حول إنتاج الوقود الحيوي في العالم أو في الجزائر أو في الدول السائرة في طريق النمو، نجد الملايين من الأبحاث، لكن في كثير من الأحوال ما تلقاش منشأ أو مصنع يقوم بإنتاج أو تطبيق هذه التقنيات على أرض الواقع، وهذا بسبب غياب دراسة تقنية ودراسة الجدوى. وهذا في هذا الإطار يجب يعني نشوف جهود من المجتمع العلمي، لأنه لما يجي المستثمر تعطيه أنت بيبر على سبيل المثال أو بحث، يعني صعب عليه يغامر بهذا الأموال في مشروع يعني على ورق. المستثمر يعترف بأرقام، بالدولارز، بالتكاليف، كم يكلف المشروع، كم يكلف استهلاك الطاقة، كم الأوتكم. يعني عادة هذه الأشياء يعني غائبة، توجد لكن في كثير من المشاريع. يعني المشروع العلمي إذا ما كانش فيه دراسة جدوى بعده يعني تطبيقه، يعني لهذا دائما فيه هذه الجاب، أو المفروض كل مشروع علمي حيكون متبوع فيما بعد بدراسة جدوى، حتى المستثمر أو الإنسان هذا صاحب الدعم يكون عنده كل المعلومات، يحس في السيف سايد، يعني حتى يكون عنده موتيفيشن حتى يمشي في المشروع. Okay, so we highlight here in the previous section some challenges that maybe is general problems that related into bioethanol industry, and here we are going to highlight some problems which is related to the technical parts. So one of the most challenges related to the bioethanol production is the ethanol inhibition. When I talk about ethanol inhibition, I will talk about the meaning of this term in details later in the presentation. And another things is the separation costs. So usually when we talk about the production of bioethanol is mainly produced by fermentation. Fermentation, maybe it will be direct fermentation when we have fermentable sugars like glucose, and sometimes we need hydrolysis of cellulose, for example. And in other cases, we have pre-treatment, then hydrolysis, then fermentation. But the main step is the fermentation of sugars to ethanol. Okay, so we have here during the production of bioethanol, we have two steps. The first step is the fermentation, and the second step is the bioethanol recovery or bioethanol separation from the fermentation broth. Usually we are using, or traditionally we use the distillation. So once the fermentation ends, the fermentation broth will be distilled using the distillation to recover or to separate the bioethanol, and this is has a high cost, and at the same time, the distillation has high cost and at the same time is high energy consumption. Therefore, separation cost is one of the most challenge that face the production of bioethanol in technical terms, and it represents around 80% of the total cost of the production when we talk about distillation. Therefore, it's very important. When you go to general public and they found, for example, bioethanol with price and petrol with a price, basically he will choose the cheap one. He will not consider maybe the environmental concern. So what we need to do, we need to make the production of the production cost of the bioethanol less, to make it more competitive to the fossil fuel. And one of the solution to look for another alternative for distillation. So distillation is the main reason of this high cost of production. Recently, there is a lot of research focusing or looking for another alternatives for distillation. These alternatives, they are cost saving and at the same time are energy saving. We can mention different techniques here. We have perforation, vacuum fermentation, gas stripping, adsorption, and solvent extraction. Some of the techniques, or we call them unconventional techniques. We have distillation is the conventional techniques for bioethanol separation, and we have this one is the unconventional techniques for ethanol separation. But the application of these techniques is still limited in the industry, and most of the bioethanol industry is using the distillation for a lot of reasons. And one of the reasons that I mentioned before, the need of economic analysis for these techniques, the need for models, mathematical models for these techniques, because the mathematical modeling can be used later for the controlling and for optimization and for other things. Okay, so I think we don't have enough time to go through this all techniques. So our focus today will be about perforations. So we said that one of the challenges that facing the integration of these techniques in the industry is the lack of mathematical models. When we talk about, especially for the fermentation, the mathematical model is very complicated. We know it's a biological system because we have here usually the fermentation process occur because we have here the yeast which ferment these sugars to ethanol. So we have here living things, biological system, and the biological system has like unpredictable behavior, which make the fermentation modeling is very complicated. And when we couple it with another system, it will be more complicated, but because we have here two systems, the first system for production, which is the fermentation, another one for separation, for example. So in our study here, we are trying to do like modeling for integration of membrane technology in bioethanol industry, and we said we take perforation as a case of study. First of all, before we start the details, just we want to present the perforation system. So the perforation system usually is concluding 5 parts. The first one is the bioreactor, here where the fermentation occur or the production of bioethanol. For example, you have here the source of sugar, which can be, for example, glucose, or can be, for example, any of the, can be corn, can be molasses, can be sugar. So, and we have the yeast inside. The yeast will ferment the sugar to bioethanol, and this bioethanol will be in the fermentation broth. So what we need to recover this bioethanol. To recover this bioethanol, we have here a pump. This pump will pump the fermentation broth here into our membrane model here. And here the separation will be a Q. Okay, so this membrane model will be at the same time coupled with vacuum pump, and at the same time with cold trap here. The cold trap here, and the retinate will be recycled again to the bioreactor. So the perforation process is clear here because of, we said that is the membrane model will be linked to the vacuum pump. This vacuum pump will create, so we will have like two sides in the membrane here. So the first side here will be the retinate, and the second side will be under the vacuum pressure. So we will have difference in the pressure here between the both sides of the membrane. We have here low pressure because the vacuum, and we have here the atmospheric pressure, which is a normal one. So we have different pressure in the two sides of the membrane. This difference of pressure is the driving force for separation of bioethanol. So what happened here? We saw that here the fermentation broth is liquid. So this liquid here, under the pressure, because the selectivity of the membrane, what happened? We have here a mixture, and this mixture here in our system, usually it has different bioproducts and ethanol, and at the same time water. So we need to separate the ethanol from this mixture. So what's happened here, because of the difference in pressure between the two sides of the membrane, the ethanol will turn into vapor phase. So, and one is, during this, we call it perforation, because the ethanol will turn into vapor. So after that, will diffuse through the membrane in the gas form. So we will receive here our gas, or our ethanol, in the form of gas. And here we have the cold trap. This cold trap is very cold, and it's used for condensing our gas, which is the bioethanol, which will be received here and collected here. So this is the description of our system. So the advantage of this system is like it's eco-friendly, with energy saving and with cost saving. At the same time, this process doesn't generate any waste, and it's easy to be integrated. Okay, so we said that our work here will focus about the modeling of the previous system we described, as the modeling is very important for controlling, for optimization, and for design of reactors, which help in the integration of the membrane processes in the industry. So as we said before, here we have our bioethanol. This bioethanol at the same time will recover the bioethanol here in the cold trap, and will recycle retentate here to the bioreactor again. So maybe the reason we said why we need to do it continuously, why we don't just finish the fermentation, then we do directly, we take all the fermentation broth and we do the separation, because as we mentioned before, the previous slide, we said that one of challenges or one of the technical factors that limit the production process of the bioethanol is the ethanol inhibition. So the ethanol here is produced by the yeast here because of the fermentation of the sugar. We'll have ethanol here, but at certain point, this product will inhibit the living cells, which is the yeast. Okay, so the yeast at certain point of ethanol cannot survive anymore. So the production will stop of ethanol. Therefore, it's very important to continuously we remove this ethanol once it's produced to make the more productivity. So this is one of the most important things why we need to use in continuous mode the perforation or other separation processes. Okay, so these techniques can solve the problem. I mean, when we conduct our fermentation in the continuous mode, we'll stop the inhibition of ethanol. At the same time, it can be alternative for the distillation, which is very expensive. But this will generate another problem. Actually, here we stop the inhibition of bioethanol and we recover it here. But here in the retentate, we don't have only water, because here in the mixture, we have water, we have ethanol, and at the same time we have sugar and some bioproduct. And this bioproduct will be not separated here. It will be accumulated again to the bioreactor. So at certain point, maybe these bioproducts can be or can inhibit the activity of the yeast or can stop even the fermentation process. So one of the maybe things that they didn't focus about in the previous work during the integration of the bioethanol separation and bioethanol production is the association between the separation process and the production process. So the separation process will lead to the accumulation of another bioproduct in the system. So this the most important or the most major bioproducts that accumulate in the fermentation system is the succinic acid, glycerol, and the lactic acid and acetic acid. So the accumulation of this bioproduct in the fermentation broth is secure. But actually, the mathematical models that we know about the fermentation, there is no model which describe the inhibition effect of this bioproduct in the system. And considering, or if we don't consider this facts, this will lead to the fail of the mathematical models that we use, and this will cause maybe loss of money and time. Okay, so there is absence of complete model which describe the interaction during the integration of the fermentation and perforation system, and this is what we have been working on in this project. So the current study was conducted with the aim to develop a new model, development model for alcoholic fermentation with regard to bioproduct inhibitory effects. And the second thing is to optimize the perforation process for ethanol recovery using RSM. We'll talk about the RSM later. And at the same time, we are going to model the separation process using solution division model for ethanol recovery. And then we integrate the model to develop complete model for fermentation, perforation integrated system. Okay, so here we can review some works which have been conducted on the integration of alcoholic fermentation with perforation process. So we can see here the most of work was conducted using PDMS membrane here, and the feedstock of the production of bioethanol was different. Some they use sorghum juice, barley straw, banana waste, glucose, newspaper waste, sweet sorghum stem. So here you can see that these papers use different feedstock for bioethanol production, and at the same time they use different operating conditions, and they were focusing more about separation factor. It means the separation factor, of the membrane, and the total flux of the permeation. But there is a lack of studies on the modeling. So most of them they were trying to maximize or to optimize the performance of this model here, selectivity or, for example, the permeation flux. But there is no study about the modeling of this system as one unit. Okay, so we can compare here, for example, distillation. I try to do is not techno-economic analysis. So we said in the previous work, previous slides that the lack of techno-economic analysis is one of the most barriers that stop the integration of these techniques in the industrial scale. So in this, I was trying to do like analysis or comparing between distillation and the other techniques that can be alternative for distillation. I was looking for techno-economic analysis research. I couldn't find like a lot. I found only two techniques, perforation and vacuum fermentation. So one of the advantages of these techniques is that it's easy to be integrated. They are not toxic to the cells. The yeast. They are characterized by higher ethanol productivity compared to distillation. And here, especially because they are conducted in continuous mode, so the productivity will be higher when we compare it to the distillation. At the same time, they are characterized by less energy consumption. When we see here the price, this comparison was conducted based on previous work. So we can see that 1 liter of bioethanol will cost around $1.4 per liter for if we use distillation, and it's almost $0.08 if we use, for example, perforation or vacuum fermentation as technique of separation. One of the limitations through this review of the work of the integration of the membrane technology in the bioethanol separation, we can see that there is lack of membrane materials. For example, if we see here in the table previous here, we see the most of works are using PDMS membrane. So there is a lack of membrane materials, low selectivity. For example, the recovered bioethanol usually will not be 100% pure. So later we need another process maybe for purification. One of the limitations is the lack of the modeling of studies on the integrated fermentation perforation system. And this is what we are going to work in this project. And another limitation is the lack of techno-economic studies to assess the integration of the fermentation with alternative ethanol recovery techniques. So we are going to work on one of this limitation in this work. Okay, so we have here, we start our work here by batch fermentation modeling. So in our work, we have 3 major steps or 4 major steps. The first one was to model the fermentation process with consideration of the bioproduct inhibition. So we are going to develop new modified model for fermentation with considering the inhibition effect of the bioproduct. Then this part will be conducted in batch mode in first. Then we go to the separation process, which is the perforation process. We need to optimize first this process to find the optimal condition using RSM techniques. This RSM techniques is like factorial design, but is a bit different because it has more features. Then once we define the maximum or the optimal operating condition of the perforation process, we'll do the modeling of perforation process using a solution division model. Once we finish the modeling of the fermentation and the modeling of perforation, we'll try to integrate the both models to build a complete model for fermentation perforation system. This model has the ability to predict what's happening here and what's happening here. So at the same time, for example, can predict what is the concentration for bioethanol here, what is the concentration of sugar, what is the concentration of the cells here, and we can know here how much is collected here and how much the concentration of ethanol in the permeate. So here is just the techniques that we use, for example, for the yeast growth or the yeast concentration. We use spectrophotometer measurement for the glucose, ethanol, and bioproduct concentration. We measure it using the HPLC, using Biorad Aminex column. So here in the system, we will have glucose, we have substrate, and we will have at the same time ethanol, and at the same time we will have the bioproduct. So this bioproduct, which we have mentioned before, is lactic acid, succinic acid, and the glycerol and acetic acid. After for the simulation was conducted using MATLAB. The performance of the model was validated using coefficient of determination and at the same time the mean absolute percentage error. Okay, so the first steps we did was to determine the concentration of this bioproduct. We saw that there is ethanol production in the system, and at the same time there is some bioproduct. So we need to know first how much bioproduct can be produced in the system, for example. So we conduct fermentation at concentration of glucose here at 100 gram per liter, and we evaluate we just measure after 3 days, we measure the concentration of the bioproducts after the end of the fermentation. So we found that the glycerol is the major bioproduct in the fermentation broth, which represents around 56% of the total bioproduct mixture, followed by the acetic acid, which represents around 36%, then the succinic acid, which represents around 8%. And we didn't find any lactic acid, even we expect that there is lactic acid in the system, but there is no lactic acid in our fermentation broth. Okay, so here, the second work was to we know the concentration of the mixture. So what we are going to do, we are going to prepare a mixture of this bioproducts and with different concentrations, and we will add it to, for example, I prepare this mixture here. I will take 56% of glycerol, 36% of acetic acid, and around 8% of succinic acid. I will make my mixture. Then I will take this mixture and I add it to the fermentation broth with different concentration. For example, I put in the first, I go to the fermentation broth, I put, for example, 10 grams of this mixture, I put 20, I put 30, I put 40 and 60 grams of this mixture to the fermentation broth in the beginning of the fermentation, and see how different concentration of this mixture of bioproducts will affect our fermentation. And we try to model these effects in the form of mathematical model. So the first thing, just we collect our experimental data, then we calculate the parameters of monad model, which is here the mu max, QS, and the yield. We measure specific growth, and we define our fermentation model, and we conduct validation. So this is our model here. This is the model for the yeast concentration. This is the model for the substrate concentration, which is in our case here is the glucose. And this is here the model for product, which is the bioethanol. And this is the mu usually is the specific growth of the yeast. Okay, so our as we see here, the substrate is related to the concentration of the yeast, and even the product is related to the concentration of the substrate, and the concentration of the yeast is related to the specific growth. So once we determine this specific growth, we can define all the other equations by knowing the initial condition of substrate and the cells concentrations and product concentration. So this is the mathematical formula of the specific growth. This is the convention or the traditional monad model. Here, this model is concentration, or is focusing about the effect of the substrate concentration on the growth, but we don't see here, for example, for maybe you can ask and you say why your concern here is about the bioproduct and why they are not included here in the effect on coefficient of growth. And you didn't talk about the ethanol effect. Actually, the ethanol usually we said that it's continuous mode. So we said that we are going to remove or recover the ethanol continuously from the fermentation broth. So we don't expect that ethanol will have inhibition effect in our system here. So our concern here, this is the normal model, or we call it the monad model. This is the classical one. And we see here is more related to the substrate concentration, but they don't take the inhibition of bioproducts into account. So our work will be mainly to focus here and to include the bioproduct inhibition factor to this classical system. Therefore, what we need to do, we need to see how the concentration of bioproducts will affect this coefficients system. So what we do, we prepare a mixture of different concentration of bioproducts, and we will see how this concentration will affect this coefficients to include our mathematical model of inhibition here. Okay, so here we said this is the normal model or the classical monad model, and we said there is a function here of inhibition that will include it. So this is the novelty of our works. So we see how the concentration of bioproducts will affect our growth coefficients. So here we know the first thing we make our boundary condition here. We know that, for example, if this F, which is the inhibition effect, if X is a concentration of bioproducts equal to 0, I mean the concentration, so there is no bioproduct. In this case, our system here will be the same, and this F, it will be here equal to 1. So because there is F equal to 1, because we don't have any inhibition effect, because X equal to 0, which is the concentration of the bioproduct. But if we have here Fx equal to 0, here X equal to 1. X here, actually, we define it like the reciprocal of the maximum inhibition and the actual concentration of the bioproducts. So we have here, we're going to assess 3 models, which is the linear, parabolic, and exponential. And because we see that we found that these 3 models can consider this limitation, as we see here. This model, they have the same boundary conditions that we have. So we are going, maybe you ask how you did get this equation. This was through the screen of different function using the library of different software, for example, like Origin Labs and other things. So through the screen of different equations, we are trying to look for the function that release our boundary condition. We define 3 of this function, and now we are going to just validate our assumption to find the most suitable model to express the inhibition effect of the bioproduct. Okay, so we prepare mixture at different concentration, and we measure here the effect of ethanol or bioproduct inhibition on the maximum or the maximum growth coefficient. At the same time, this coefficient of here, we found that the maximum specific growth decrease with the increase of bioproduct on concentrations, and the total or the maximum inhibition was at 60 grams per liter of this concentration. So this here where the fermentation will totally stop. So we try to model this effect. We validate the model, or we compare the model using the 3 functions that we defined previously, which is linear inhibition, exponential inhibition, and parabolic inhibition. And we found here that the exponential model was the most fitted for our experimental data. So our inhibition effects function was defined like exponential function, and we define here this factor as coefficient of inhibition of bioproducts. Okay, so this is our new model. So as we know, this is the traditional or the classical monad model. We did modification by including new term, which is bioproduct inhibition effects, which is exponential. So, and we calculate this QZ, which is the coefficient of inhibition. So once we define the model here, now we want to conduct validation of the model to compare the performance of the model with the performance of the classical monad model. Okay, so this is the yield coefficient and the model, our model here. So this is some data that experimental data. So we finish the modeling and we conduct experimental works to validate this model, to compare the experimental result with the simulation result, and to compare the classical model with the new modified model. As we see here, we conduct the validation at different initial substrate concentration, the glucose concentration. So we conduct it at 1 gram per liter, 100 gram per liter, 150 gram per liter, and 200 gram per liter. As we see here, there is not a big difference between the classical and the new modified model here, as we see here. But this difference, it was too small. Here is too small, and the same here. But this small difference is gets bigger by increasing the initial concentration of substrate. And this is understood because we know that if we have more substrate concentration, we will have more bioproduct. And when we have more bioproduct inhibition effect, we will see that there is more inhibition, or there is more difference between the both models. And we see that here, even there is not so big difference, but the accuracy of the new modified model was higher relatively when is compared to the classical model here, which we call the monad model. But this is understood because we conduct the validation in batch mode. What does it mean batch mode? It means it's not continuous mode. It's just we put sugar and we conduct the fermentation, and for example, for just 3 days or 2 days, and we did our analysis. So in this case, this result is expected because we will not have that much of bioproduct in the system. The bioproduct usually is characterized or we can find it in long-term continuous fermentation. Therefore, we will focus only about the development of the model. Then, when we finish the development of the perforation system, then at the end we will see our system, the difference between the system in continuous fermentation. So this model, the new developed model, will show more difference compared to the classical one when we conduct the continuous fermentation. Okay, so now we have completed the development of our models for the fermentation, which
Dr. Hamid, I appreciate if you can speed up a little bit because we are running out. We are exceeding estimated time.
Okay, sure. Sorry for delay. Okay, so we have finished here the modeling of the fermentation. Here, because the time I won't skip this, was only for optimization of the perforation process. We define here the optimal condition of perforation. So we define our condition. Then we have conducted our perforation for modeling using solution division model at the operating condition that we defined previously in the optimization. So here we calculate the activation energy. We calculate, for example, here the partial or the permeability of the membrane for ethanol and water, because we consider in the beginning that the mixture of the fermentation broth is water and ethanol and water. So once we define the permeability of the ethanol and water and the activation energy for both elements also, we can define our perforation model. So now we have fermentation model, and we have at the same time the perforation model, which is the separation system. We just integrate the both models to see how the complete model can predict the both data of fermentation and the separation. As we see here, we see that our model in blue color, which is the developed one, our new model is showing higher accuracy compared to the classical one for predicting the ethanol concentration. Okay, so here we can see here we said previously that we didn't notice such as big difference between the classical model and the new modified model in the batch fermentation. But here, when we see in continuous mode, we see that there is a big difference here. So, and at the same time, we can see that the new developed model is more accurate. When we see, for example, for sugar concentrations, this is our model. This is the experimental data, and this is the conventional model. The same thing here for the yeast concentrations. We can see that our model is more accurate here. And this is because, and we see that here, when we notice here, in the beginning of the fermentation, the both models were too close. But by the time, the difference is get bigger. Because here, the concentration of the bioproduct in the beginning of the fermentation was very low. Therefore, we don't see any inhibition of bioproducts. So almost our model perform like the classical one. But here, once the bioproducts start affecting our fermentation, we can see the difference between both models. The model also was used for the prediction of the permeation of lags for water and ethanol, and it showed like higher accuracy for predicting the permeation. Okay, so conclusion and application. So the complex model, which was built by combining the developed models of both fermentation and perforation process, indicates a high reliability one was tested and validated against experimental data of fermentation and perforation data using fermentation perforation integrated system for bioethanol production and recovery. Indeed, the developed model will represent an effective tool which may be used for prediction and control of continuous fermentation with high accuracy during the production of bioethanol. This will lead to the integration of the continuous fermentation in the industrial sector, which is currently preferring batch mode due to the challenges and difficulties of controlling the continuous fermentation, which may lead to low productivity and reduce the profit. Okay, so this is some recommendation for and future trends. So we need more to turn on the light because here we quantify we model the effect of inhibition effect, but we didn't define how the mechanism of inhibition occur. So we need more effort or more works to put light on the mechanism of inhibition of bioproducts. At the same time, in this work, the following problem was limited in this present study, but in case we have, because I use glucose as substrate, but if we are going to use some agricultural wastes, for example, in this case, maybe the following problem can be cured. Therefore, we need maybe to take in consideration for the next model the following problem when we model the perforation process. Further efforts are required to synthesize new materials for membrane separation for perforation application. As we have seen before, only the PDMS membrane was used in the majority of the previous work. At the same time, hybrid system based on coupling different separation technique can be used to get more or higher purified ethanol, because we said that usually the ethanol that we collect is or has low concentration. So if we manage to hybrid some separation process together, we can produce higher concentration ethanol. Okay, so this is just summary of everything we present in this work. So this model, which can predict or show 15% higher accuracy compared to the previous classical models, this can help in increasing the productivity of the bioethanol, at the same time is to reducing the cost of production and at the same time the recovery. Thank you for attention. I open the window for questions. If you have any question from the audience or from the moderators.
Thank you
I'm
very
sorry
much
for the long term.
No problem. Yeah, thank you very much for your detailed presentation. I think it's very important in Algeria to consider biofuel and bioethanol as an energy or source of energy in our new energy transition. You know, it's not only oil and gas or geothermal, but even biofuel. I was so surprised that you said there is no studies done so far in Algeria about this matter. So
yeah.
really
Actually, just want to make there is studies, but I mean there is no production in Algeria. When I try to find the statistic about Algerian production of bioethanol, is zero.
Yeah,
but actually there is a lot of Algerians working in bioethanol production.
Excellent.
Yeah.
So it's very important to bridge the gap between academia as well as the industry. So we're going to pick up a few of your questions in the comment sections. We have so many questions. Let me just pick the first one. First one from Jamaluddin Ayush. He's saying ethanol is the second gas causing the global warming effect, warming after CO2. So, is the ethanol production going to have any negative impact on in the atmosphere? I would say.
Yes, the thing that here we didn't say that ethanol will stop because all the kind of I didn't say all, at least the biofuels, actually they produce also the carbon dioxide when it's during the combustion, but they are reducing this emission by almost 50%. And as I said during the presentation, one of the most problems maybe related to the ethanol production is that deforestation to make land for production of bioethanol. Therefore, I was emphasizing on producing the bioethanol by recycling some wastes from the agriculture or from industry. But actually, that doesn't happen. Yes, and I am agree about what he says.
Yeah, thank you very much. I'll pick up the next question. It's written in Arabic from Bilal. في تحدي آخر تعاني منه الجزائر هو الأمن المائي، فهل تتوافق زراعة الذرة بكثافة دون تهديد الأمن المائي في الجزائر على المدى البعيد؟
نعم، من خلال نفس النقطة اللي يعني توجه بها الأخ سابقا. الإيثانول إذا كان المصدر صناعة الإيثانول هو عن طريق الزراعة، هذا يمثل تحدي للجزائر والدول، خاصة والدول السائرة في طريق النمو، لأنه هذه الدول تواجه مشاكل في خصوص الأمن الغذائي. وعادة زراعة هذه الزراعات الموجهة لإنتاج الإيثانول تكون تحتاج إلى مياه وتحتاج في نفس الوقت إلى أراضي زراعية، وهذه الأراضي الزراعية تكون على حساب أراضي للزراعات معاشية. لهذا يكون الخيار الأفضل هو إنتاج الإيثانول من بقايا زراعية أو بقايا الغابات أو بقايا صناعية. وكان عندي تجربة بسيطة في إنتاج في الجزائر خلال دراستي الماستر، إنتاج الكحول من خلال البقايا الصناعية للسكر اللي هي اسمها المولاسز. كانت فيها. لهذا من الأفضل التوجه على الأقل في هذه الدول إلى مصادر بدون تمس الأمن الغذائي أو الأمن المائي.
البقايا
نعم. لما نشوفوا على سبيل المثال البرازيل أو بعض الدول تعانيش هذا الأزمة. لهذا كانت قطعت أشواط في هذا المجال، عندها زراعة مخصصة للبايو إيثانول. لكن بالنسبة للدول الأخرى اللي عندها صعوبات المائية أو صعوبات الأمن الغذائي، من الأفضل هذا الخيار يكون يعني أسوأ. لهذا يكون الصناعة من البقايا الزراعية أو البقايا الصناعية هو الخيار الأفضل.
شكرا على الإجابة. ناخذ سؤال واحد آخر من comment section. Thank you for the topic. As far as I know, biofuel is produced from remaining of bioorganic matters. So how can this create? Yeah, that's what we were just talking about. How can this create a problem for food supply? It's this is. I mean, I think you already answered this question. But if you want to add any comment, he thinks that biofuel is a recycling of the remaining parts. So how it can create a food problem if it's recycling?
Not really, actually. There is yes, can be produced by recycling or from wastes, but the actual production of the world, I mean, when you go to Brazil or other countries, the majority of the production is from crops. I mean, agricultural crops. But the best option, as you said, is from recycling, but it's still limited. Therefore, we need more effort to encourage. I mean, scientific community, we need more effort to optimize, to encourage the industry guys and the policymakers to establish programs and industry from the West.
Thank you very much, Dr. Hamid. We'll take another questions. We had so many questions and comments actually here. From unknown user in YouTube, he said, Salam and Sahar Ramadankum. So this is actually a question from many questions in different comments. Ilyas from Algeria, Marine Superintendent in Shipping Industry. I have a question about the economics of the bioethanol. If you compare the heat contents of the diesel and the bioethanol is 45 and 50 and 30 kilojoule per gram, which means to store the same amount of energy, you will need 40% more space. Now, question 1, in percentage, how much less CO2 is produced compared to the classical fuel, diesel, for example? And question 2, how far are we from an economic viable price of bioethanol in terms of BTU USD, if possible? And thank you all for the initiative and the detailed presentation. So I will display the first question, maybe, if you can take it. Percentage of how much CO2, yeah.
Okay, for the percentage of how much CO2 reduction compared to the oil is almost 50%. I mean, when they consider, like, when you do this comparison, usually they consider that the bioethanol will not produce, for example, more energy like the oil. When they compare, usually they see how much, for example, if oil will give, for example, I don't know, a kilo, for example, will produce kilojoules, they will see how much emission will be produced with this quantity of energy. So they compare usually the energy. It's around 50% reduction of the emission. And when we talk about the economical cost of production, 2 days, I think we have conducted like a comparison between economical cost for distillation and what we call it perforation and vacuum fermentation, but we didn't compare about the production of oil. But what I know, that production of oil, I mean, is less expensive compared to the biofuel. Therefore, we can see that we need more effort to, and this is what we are trying to do, to optimize the process, to provide mathematical models, and to optimize these alternative techniques to make the bioethanol production costs less. But currently, the production of oil or the oil is less expensive compared to bioethanol.
Yeah, I think this is quite understandable as it's a new energy. You know, we still need much research and years of development and research get it better and better. So with that said, I will not take all the questions. I apologize if I couldn't take all the questions because we are really running out of time. Again, thank you very much, Dr. Hamid Zentou, for the very interesting presentation and sharing with the public about the biofuel solution. Thank you very much for your accepting our invitation. I also would like to remind you that we are going to have another webinar in geoscience this afternoon at 3 p.m. 2 p.m. Algerian time. It will be a different project, earthquake hazard mitigation, where we are going to have Professor Mustafa Maghrawi, who is going to discuss the lesson learned from previous earthquakes. So please don't miss the webinar. Again, thank you very much, everyone, for your attendance, and thank you, Dr. Hamid. Thank you very much.
Thank you very much. Thank you very much. Thank you.